In this video, we are going to discuss scalar and vector fields. What is field? If any quantity that will vary over space, then we can say that one field will exist. Like if I say that one temperature is varying, temperature T is a function of space. Space means the x, y and z, these three direction. So I can write in this way, this is your x direction and it is y and it is z. So within this space, within this region, if temperature is varying, it's a function of x, y, z, then I can say that it's a field of temperature. Or if the electric field E, that is a vector quantity that is also varying over space x, y, z, then also I can say that a field will exist, and that is for electric field. Similarly, we can have magnetic field H vector, and that is a function of x, y, z, or gravitational field, the G vector over x, y, z. So there are several such example of fields which are function of space. Okay. Now this total field we can classify in two ways. One is called scalar field, another one is called vector field. Okay. Now the scalar field, there one scalar quantity will vary over space, like this one. This is a scalar field. Temperature variation is a scalar field. Okay. Like temperature, we can have other things like spacer field, okay, density field, all those things. And these are the example of vector fields. Here vectors, it is not only having the magnitude, it is also having the direction. Now in this video, we will try to understand how to represent the scalar fields and how to represent the vector fields in a graphical way, and what operation we can do on scalar field and what operation we can perform on vector fields. That we will try to understand here. Okay, so let us start with scalar field in detailed way. So what is scalar field and how to draw the scalar field? So this is our task. So one example already I have said, that temperature. Suppose if we consider one room, so here we are considering one room. Okay, and this dimension, this side is, suppose if it is 6 meters, and this side the room dimension is 10 meters. And at the middle of this one, the temperature, it is given by, suppose it is 10 degrees centigrade. Okay. Now if I move from this middle point, so if I go to this side or this side or this side, everywhere, so suppose it is seen that the room temperature is increasing on xy plane. So remember, this I am plotting here, this direction is x and this direction is y. We are not going to consider vertical height right now. On xy plane on the floor, I want to measure the temperatures. So at the middle the temperature is 10 degree. So if you go away from the middle, suppose here, so if I consider the temperature at this end, and if we find that it is 20 degrees, suppose, so at this end also it is 20 degree. Like that, in these points the temperature is always 20 degree. Okay, so on these points everywhere the temperature is 20 degree. So that also we can find it in that way. Similarly, if we move far away, suppose like this point it is 30 degree. So everywhere on this point, these are 30 degrees. Okay, this is the curve for 30 degree. So these points are called level set or contours or levels. So this function is having, so this temperature, I can write temperature T is a function of x and y only. And for this example, if this is the origin 0, 0, if I consider, so at this middle point, middle is here, this is 3 and this is 5. So at this point, the value is minimum, is 10 degree. So can I have this kind of function? So can I write that it could be x minus 3 that square, okay, and plus this y minus 5 that square plus 10, this kind of, okay. So if this is the function, then you can see that at t at 3, 5, at this one which is shown here, so this will be 0 and this value is 0. If I replace x by 3 is 0, and this is also y replaced by 5, it's 0, and this is 10, so total is 10. So at 3, 5 it is 10. Similarly, I can find out at certain point, suppose t at, suppose if I write 4, 6, what is the value? So I replace, this is 4 minus 3 that square plus it is 6 minus 5 that square plus 10. So meaning is that this is 1, this is also 1, this is 10, its total is 12. So at this point it is 12. Similarly for other points also we can get some other point where the function value is again 12. So if I connect all the temperature 12, then I will get one line. That line is called a constant temperature line. That is a contour plot. Like here I have shown that this green one is the temperature of 20 always, and this one is 30 degree everywhere. Okay. Now this kind of scalar field we can plot in 3D because it is in 2D now. This function is function of x and y. So we can go for one axis, z axis, to represent this function t of x and y. Okay, that I can show you. So if I draw it, then what I will get? So I will draw this function. Okay, this is your x axis, this is y axis, and this one is z axis. And z axis we want to show this t of x, y. And we have seen that at this point, okay, at this point the value is, so this is your 3 and this one is 5. We can have the temperature is minimum is 10, so that I can show it here. So this value, so I can show this thing little bit compact way. So this value is 10. Now if we move from this point, center point, everywhere if we go, the temperature is increasing. Okay, so this side temperature is increasing, this side also temperature is increasing. Okay, so if you draw it neatly, so it will show you one kind of bowl shape. So you will find these things. So this is the surface, so this side. So on this is on xy plane. Now what I said that so this is the point, we are getting only one point which should show that temperature equal to 10. Fine. But if I say that temperature equal to 20, okay, if I want to go for one section, this is for 20 suppose. So at this point I can have one horizontal cross sections like this. If I go for, so it will cut here. So this could be here. So you will at the edge, this is the edge, and this one. So on this line, everywhere the temperature is 20. So I can say it is 20. So if I map it in on xy plane, if I take a projection on xy plane, we will be getting one such contour. Okay, so that I will show in this way. So this is around this point, center point. Similarly, if it is for 15, I can have smaller one. And so this is for 20, and this is for 15, and this is at 10. And if I go for a higher one, so we can have this kind of contours. This could be for 30 degrees centigrade, like that. Okay. Now I'll show you the 3D pictures in Math 3D plot. So I have used Math 3D plot to show you this kind of function. Okay. So let us see this one. So here I am going to show you f of x comma y, which is nothing but x squared plus y squared equals to plus 1. Okay. So its minimum value is 1. 0 plus 0 equals to 1. Because this function, the x squared cannot be negative, y square cannot be negative. Its minimum will be 0 plus 0 and 1. Okay. So let us see these things. Okay. Now, so to see this one, now here you can see that I am showing you this is the x-axis, this is y-axis, and vertical height, this z. There I am plotting this one, f of xy. So z is nothing but f of xy, it's x square plus y square plus 1. Okay. So you can see that its minimum is at origin 0, 0, and its height, minimum height is 1, and both sides it is increasing. Right. So this is the function. Now here the most important thing is that this kind of scalar field, if it is given, we will try to understand which direction it is increasing rapidly. Okay. And because of, based on this one, we will try to understand what is the gradient. So here we will perform one thing that is called gradient operation. Okay. So we will see this one, grad of this f of x comma y comma z, and that will give you one direction at which the function is increasing rapidly. So that will be discussed in detail in another video. Right now I will be showing you more such figures, scalar field and vector fields. But one important thing I am showing you that, telling you that we can perform gradient operation on scalar field, then we will be getting a vector quantity. So this will give you one direction at which function is increasing rapidly. So it's a vector quantity. So then you will be getting a vector field. So if I use gradient operation on scalar field, we will be getting another vector field. Okay. Now I'll show you more example. So this is the one function, x square plus y square only. Okay. And you can see that. So this function, I think I have drawn it x square plus y square, and it is at 0 is 5. So it should be plus 5. Okay. It's okay. And now you can see I have also drawn the contours at this point. These are the contours for this 3D plot. So j is the function of xy, x square plus y square plus 5. So, and these are the corresponding contours. Okay. And I can show you the contours in separately also. This way. So this is, you can see that this is the x, this is y. At this point it is minima 0, 0, and as we are moving in this direction, it's increasing. So this contour plot, it is for 5.1818, and this is the higher one, 5.3636. Right. Next one is 5.5455. So these plots I have got from MATLAB. Okay, I have drawn it on MATLAB. That you can also draw it. Okay. So you will see that the function is increasing on all the directions radially. This is the important concept. Right? It's perfectly radial kind of thing. In every directions, it's equally it is increasing. Whether x, y all directions, it is increasing equally. Now, if I consider one function like this, j equals to x square plus y square by 4. Now, you can see that as x is increasing, the function is increasing rapidly, but as y is increasing, this is increased by 1/4 of x square, right? So, if you increase in y direction, it is not increasing that way. That is reflected here. You can see that this is the x direction. If you move from x equals to 0, this side, it is increasing rapidly, parabolically, and this side also it is increasing rapidly. But if you move from 0 to this direction, it is increasing slowly, like that, because its 1/4 multiplication is there. So its contour plots looks like this. So its contour plot is no longer circular. In this case, these contour plots are elliptical in nature. And you can see that if there's a little change, so you need to understand here what is the meaning of this contour plot. Okay, now I'll tell you here. So this is the middle point. Can you see? This is 0, 0. At this point, minimum value is 5. Now Ax is increased up to this point, and this is my x increment. And suppose if I consider this point here, if x is 0, by y is this one. So what the value y? So y is around 0.6. So at this point I can write it is 0, 0.6, and this point I can write it could be from the figure whatever it is showing. Okay, so it is may not be exact one. So it is 0, it is 0.3. It could be, right? So what is the meaning? Meaning is that when x is increased by only 0.3 and y is kept 0, then the function j is increased by this factor 5 to, it's increased to 5 to 5.1136. So this much increment is there, and because of this 0.3 increment in x. Okay, whereas this one, if we keep x constant, if we increase the y only, then we need to increase the y by 0.6. Okay, then only we will be getting the same result, 5.116. Meaning is that if x is increased by only 0.3, we are getting the same result. But whereas to get the same result, we need to increase the y by 0.6. Means on x direction, function is increasing rapidly this way or this way, whereas along y, the function is increasing this way. It's almost flat. Okay, so it will give you certain idea in the, so which direction it will increase and what rate it will increase. So this is important concept. Try to understand this one. It will be useful. Next class or otherwise in future videos we'll be discussing the gradient thing, and there you will be getting better, more concept. Okay, I'll show you one more complicated function j. This is the function e to the power minus square root x square plus y square cos 4x cos 4y, and you can see that at x equals to 0, y equal to 0, it is having a mixed maxima, this point, and it is decreasing initially on the other side, and it is going to the minima, local minima in these few points, then again it is increasing this side. Okay, and those contour plots I have shown here. Can you feel these things? So okay, you can see that here, this is the middle, at 0, 0, the function value is maximum, and that maximum value, it could be 0 plus 0 is 1, it could be close to 1. Okay, so this point, I can show that point here, this point, its magnitude is 1, okay, at this point, and if we move from this point, all the directions, the magnitude is reducing, so it is becoming, so you can see that its value is reducing, and it is not only reducing, somewhere it is becoming negative. You can see it is negative. So here it is negative. So this is a 0 line. Okay. Okay, it is going below the 0. So here it is negative and it's a minima. Minima is around minus 0.5 kind of things. So that minima point we are getting here. This is one minima. Again we are getting one minima here. This is one minima. This is minima and this is minima. Is it okay? So here again you can see that this side again it is increasing little bit. This from here to here, this side again increasing. It's increasing, and this side if I move, it's a decreasing function. So this function is showing some characteristics. One side it is increasing rapidly, other side it is decreasing rapidly. Okay, so if we use gradient concept, then we can understand which direction it is increasing rapidly. Okay, that thing will be discussed in detail in another video. Now we will move to the vector field. What is vector field? Vector field function f, it's a vector quantity. It will vary over space. Space means a function of x, y, z. Okay. So far you will take few examples. I already have said that electric field, magnetic field or gravitational field all are vector fields because they are having directions along with the magnitudes, right? Now if I start with a simple one, that is called uniform vector field. What is the meaning? Meaning is that it's a vector field. Field will exist on the space, but its value is not exactly depending on x, y, z. It's a constant. That will be called uniform vector field. For example, if I say this f vector, I write x, y, z, but essentially it is a constant. And if I say it is 0 times x direction, x unit direction, and 1 times in y direction, and again 0 times in z direction. So what is the meaning? Meaning is that this vector field is having only one component along y direction, and that value is also constant. This one is constant, another it is absent. So can you draw this vector field? Okay, so I'll try to draw this vector field. Listen it carefully. So I'll draw these things. So first I'll show you the axis. So these are three axes. This is x, it is y, and this one is z. Right? Now I have said that this vector field f, it is along y direction, this direction. Okay. Now at x equals to 0, the value is 1. So I'll take different color. So here also the magnitude is, suppose I'll show it in this way. At this point, when x equal to 1, then also it is 1. So everywhere this vector direction is along y. Okay. Now not only this, in this side as well, if I consider negative x, then also it is not a problem at all. Okay, these negative directions, there also will be getting same vectors. Okay, same thing. Now if I consider at y equal to 1, suppose here this 0, 1, 0, there also same thing. So I'll show in this way. So you can see that it shows all the vectors the same strength. So the length will use the same length to indicate that magnitude is same and it is along y. So not only this, I can have on vertical height, so that one I will consider this way. So this is the vertical height. Okay. So there also everywhere you will find the same thing. So I can draw in this way. So here this is the directions along y. Is it okay? So now this vector field, right? So these are all the vector fields. So you can see that I can draw it more. It could be here. So this is a uniform vector field. directed in y direction only. Similarly, we can have x direction. So I can have the vector field F, which is suppose 1 times x vector and 0 times y vector and 0 times z vector. So that vector field, easily we can draw it. So this is x, it is z, and it is y. So this time what will happen? The vector is directed along this x. So for all y also it is like this. It is directed this side. Okay, not only this, it is also here. Similarly for vertical height. So if you have the different height here, there also you will be getting the same direction because it is independent of that one, again along x. So this is a uniform field. It is directed towards this x direction, and everywhere the field magnitude is same, right? So similarly we can draw the other one. So I'll take one interesting example and I'll show you these 3D figures. Okay, just wait. Now if I consider one vector field like this, x, y and z, and that is suppose minus y x vector plus x y vector, and there is nothing, 0 z vector. Okay, so can I draw this vector field? How can I draw it? Just see. So I'll take these 3 axes. Listen carefully. This is x, this is y, and this one is z. Okay, now I'll consider this one. Suppose if I consider on x axis, y equals to 0, everywhere 0. Okay, so if I consider at origin, you can see that at origin every value will be 0 because y equal to 0, x equals to 0, every value will become 0. At origin there is no vectors. Okay, magnitude is 0 only. At x equals to 1, means 1 comma 0, what is the value? Okay, so at this point at 1 comma 0, so x equals to 1 and y equal to 0, so you are having, so I want to get this thing f of 1 comma 0 comma 0. So what is the value? So this value y equals to 0 is a 0 x vector, and x equals to 1, this x value is 1, so it is a 1 times y vector, and it is 0 z vector, that is fine. Okay, so this one I can put it at 1 0 0. So 1 0 0 is this point, there it is along y direction, so I can put a direction like this along y. Is it perfect? Similarly, so this point is 1 comma 0 comma 1 0. Okay, next one, suppose if I consider another, okay, same thing, same color, f 0 comma 1 comma 0. So what is the value? So this time x is 0, means this is 0, but y equals to 1, so y equal to 1 here, so minus x vector plus 0 y vector and 0 z vector. So what is the point? Point is 0 1 0. So 0 1 0 is this point. Okay, at this point what is the direction? Direction is minus x. So this is a positive x direction, this is a positive, so its negative x direction will be parallel to this one in negative side, so I can draw it this side. Am I perfect? Okay, now can I draw the next one? So I should go for this negative as well, little bit this side. Okay, now if I consider f F, suppose minus 1, comma 0, comma 0. What is the value? So if I replace x by minus 1, so this will be minus 1 and another 0. So 0 x vector, and this is minus 1 times y vector and plus 0 z vector. So at, where is the point? This is the point, minus 1, comma 0, comma 0. This is the point. At this point, so this is minus y direction. So this point, this is a positive direction and this is a minus x. So direction will be like this. Am I correct? Similarly, if I consider f 0, comma minus 1, comma 0, so this is the point. At this point, it will be, so it's minus minus plus. Okay, so it's a positive x direction. So it's a positive x direction. Can you check? So this is interesting. And now suppose if I consider one more point, f 1, comma 1, comma 0. So what is this vector field? Okay, at this point. So this is y x equal to 1, y equal to 1. So it is a minus x plus y and plus 0 z vector. Okay, so what is the point? 1, comma 1, comma 0. This is the corresponding point is here. So I'll take another color to show these things. So this is the point. And this direction, one is positive y and negative x. So it will be, it's neither, it's a 45-degree width. So this is your y and this is your minus x. So its addition will be like this direction. So it will be directed like this. Okay. Similarly, at this point, it will be directed like this. At this point, it will be directed like this. At this point, it will be directed like this. So you can see one kind of rotation is happening here. Right? So it is independent of z. So you can find that in vertically also it will be same things. So if I consider z equal to 1, so f 1, comma 0, comma 1, it does not matter. It is same as f 1, 0, 0. Okay. So along z it is not varying. The nature will remain same, circular. So I will show you all the figures and you can enjoy these things. So let us see this one. I hope you have got this idea. And one more important thing is that here also I can note that. So this, suppose f2, comma 0, comma 0, if I consider. Can I consider another one? f2, comma 0, comma 0 means this point. What is the value? The value will be the 0 x vector and 2 y vector and 0 z vector. So again it is along y, but strength is now double, is 2. So that thing I will show it in this way. It's a double length. Similarly here it will become double length. Similarly here it will be double length. Similarly here it will be double length. Okay. Again this side it will be like this, double length. Again this way. Okay, and you can find some kind of circulation here also. Okay, so let us see these vector fields. I'll show you in 3D plot. So here you can see that I am using Math 3D software. So 0, 1, 0, this uniform vector field I am showing here. So you can see that it is directed along y direction. It is along y direction. This is y. So can you feel this thing? This is your x direction. This is x. This is y. And it is directed along y. Okay. This is the y direction. This is the x direction. This is x. Now if I consider 1, 0, 0. So obviously it will be x directed in this direction. It is again uniform vector field. It's independent of z. That's how in z direction also it is same thing. It is not depending on x and y. Okay, it is directed along x direction. It's a uniform vector field. Now if it is 1, 1, 0, so what will happen? It is also a uniform vector field, but it is on the xy plane, but the direction is 45 degree with x-axis and 45 degree with y-axis, this diagonally. Okay. Now if I go for some non-uniform vector field, if I consider 0, y, 0, that we have considered. Okay. Now you can see that this vector field is now, it's directed on y, but close to origin, the magnitude is lesser. Okay, and if we move away from the origin along y direction, the strength is increasing because it is y. So here 1 it is 1, at 2 it is 2, at 3 it is 3, like that. The strength is increasing as we move along y direction. Right? Now if I consider the x, y, 0, so then both sides is increasing. Can you feel these things? In x direction or y direction? So it's a diagonal on xy plane with 45 degree, but strength is increasing as we move from origin. Okay. Now I'll consider that example. It's a minus y times x vector and x times y vector and z. Now can you see this kind of that circulation that we have shown earlier? It is rotating in this side, so you will get the better view if I consider vertical projection kind of things, vertical view, this kind of. This vector field is varying. This orientation is almost circular. Okay, and it is not a function of z right now. And if we put certain z, or suppose if I make it just opposite one, this is y and it is minus x. Can you see? The rotation will be just opposite. It is now clockwise manner. Earlier it was anti-clockwise, now it is a clockwise. Can you see? It's a clockwise. This side, it's rotating. Okay, this direction is this side, this side, this side, like this. Okay. Now if I consider along z as well, so with vertical height, if it is increasing, that time this magnitude is also increasing. So it is not that along z it is constant. So that's how it is little bit upward kind of things. It's rotating, but it is again upward kind of things, little bit. So these are all vector field. I have given you lots of examples of vector field, and next class we'll be discussing how to use this, how to consider this kind of scalar and vector fields. And you can note that in vector field we will discuss the divergence of the vector field del dot f, and we will also consider curl of the vector field. We will define these two things. This is called divergence and this is called curl. These two will define for the vector field, and divergence will give you one divergence value only. So it will give you one scalar quantity. So if I take a divergence of a vector field, we will get a scalar field. Whereas if I take curl of a vector field, again we will get another vector field. Okay, so those things will be discussed in detailed way. So keep watching. I hope this course will be interesting, and we will move slowly. First we will go for the line integral, okay, f dot dl. Then we will consider the surface integral, f dot ds vector. Then we will consider the volume integral, f dv kind of things. And then we will see that what is the relation between line integral, surface integral and volume integral. There we will consider divergence theorem, Stokes theorem. Then we will define the divergence and curl. Okay, so keep watching. This course is little bit difficult, but hope if you go through all the lectures sequentially, you will understand it. So thanks for watching. So I'll make more videos on this topic. Thank you.